Now let us derive the expression for circumferential stress sigma c and longitudinal stress sigma l. So what is the equation? What is the equation for this? In terms of pressure inside the cylinder, diameter and the thickness. Okay, so there are three terms here: pressure inside the cylinder, diameter of the cylinder and the thickness of the cylinder. In terms of this we need to derive this. Okay, and you will see that here, if you call this diameter small d, we will call this as diameter small d. So this is PD by 2t, this will be PD by 4t. So I am just writing this. So this you have to derive now. Okay, so you are trying to derive these equations in terms of pressure inside the cylinder. So there is a cylinder like this whose diameter is d, and the thickness is t, and the thickness of this is t, and the pressure inside is P. Okay, in terms of this we need to derive. So how much is the circumferential stress? You know that, you just understood that there will be a stress which actually tries to increase the circumference. There will be a stress which actually tries to increase its length, which is called a sigma L. We need to derive this in terms of this pressure inside and the diameter and the thickness. So let us now consider the cylinder like this, basically. So there is pressure inside, here. So this pressure inside, let us imagine that it actually breaks this into two pieces, and that is called the bursting pressure. So let us imagine that it's trying to burst about this point. And when it tries to burst about this point, you can imagine that the cylinder would feel like it is like this. It has got a thickness here like this. So I am drawing this cylinder like this, and the cylinder looks like this. And the cylinder looks like this. So that means I am trying to draw the half of the cylinder here, basically. Okay. So here the cylinder looks like this. And here the pressure acts here, no? And the force with which it wants to separate, suppose if I call this as the bursting pressure, FB, which is the bursting force which exerted, which actually separates this. So suppose if the cylinder is made into two pieces and if there is pressure inside, if you want to hold the cylinder together, the force that is needed is actually is equal to the bursting pressure. Suppose if the bursting pressure is more than the pressure that you apply, then the side will come out. Now to find out that, what you need to know is, you need to know this area. Now this area is actually useful for, because though the pressure is like this, now when the pressure is like this, it is not trying to burst. It is trying to go like this, which will balance out. Now when the pressure is like this, it is unbalanced force which will try to lift. And effectively, you can take this area. So of course, it feels that it is acting on the circumference, but you can imagine that it is acting on this area. And normally, you can imagine that it is acting over this area normally. So it is like this. So you can imagine that it is acting over this area normally instead of imagining that it is acting here. So the pressure, you can imagine this to be acting on all this surface here. Okay. Now what is the area of that surface? So can you tell me? What is this length basically? It is diameter. And then here you can call this as the length. So here in the equation there is no length term, because the length can be anything. Okay, what matters is the diameter. Okay, now anyway this length terms will cancel out. So here the area is diameter and this is the length. So you can say that here also, this is the diameter, this is the length, and therefore you can say that it is the area which is to which the pressure is applied. So now what is actually pressure? Basically pressure is equal to force by area, and if you want force, it is pressure into area. So pressure inside the cylinder So I'll call this F as the bursting pressure. I'll call this F as the bursting pressure, FB. Okay, FB. And then it is pressure into area, pressure into area. What is the area here? D into L. Okay. So you can write small d or capital D or whatever. Okay, that's the bursting pressure. So FB is the bursting pressure. Please write this. Sorry, bursting force, sorry. Bursting force. And this is the pressure inside, and FB is the bursting force. FB is the bursting force. Now, this is trying to separate these two pieces out, but what is actually holding is this area. Now, this point of, this is the metal which is actually trying to hold this thin sheet of metal here, which I am trying to show this with blue color, that is actually trying to hold it together. So it is like, we have already seen for a metal which is under tension like this. What is the formula for tension? What is the formula for stress? Stress is equal to what? Okay, stress is equal to force by area. Stress is equal to force by area. So similarly, you can say force is equal to stress into area. So now you can say that here, if this is the stress that this is taking in this direction, which you can call it as the longitudinal stress, because it is taking along the circumference. See here, it is taking along the circumference here. So you call this as the longitudinal stress. You call this the longitudinal stress. So this longitudinal stress is bursting force divided by area. Bursting force divided by area. So bursting force FB will be equal to sigma into area. So therefore you can write this as sigma L into A. Sigma L into A. Okay, sigma L stands for longitudinal stress. Okay. Now what is actually the length of, what is actually the area of this? Can you tell me? Now what is the area of this basically? What is the area of this blue colored metal? What is the area basically? What is the area which is actually trying to resist this? So can you tell me what is the area? So what is this basically? What is this basically? It is thickness. What is this basically? Length. So this is length. So this length into thickness will give you area on one side. If you want area on two sides, it is 2 into TL. So area you can write it as 2 into L here. So FB is equal to sigma L into A, which is actually how much? Is 2. Area is 2. So one kada area one to TL. Area is T into L. Area is T into L. So if it is on both sides, it is 2 into TL. So here we have said the bursting force is already equal, given by this equation. We have got one more equation here. You can call this equation as 1. You can call this equation as 2. Equate this 2. Equate this 2. When you equate this 2, what do you get? So you got sigma L into 2TL is equal to PDL. So L and L cancels out, and you get sigma L, which is equal to PD by 2T. Okay, this is what the first equation that we were expecting. So that means, I wrote this as the circumferential stress. No? So I wrongly wrote it as sigma L. This is sigma C. This is sigma C, circumferential stress. This circumferential stress. Okay, this is, I wrongly wrote it as sigma L. This is actually along the circumference, so it is sigma C. Okay, I think I need to make this video once more maybe. Okay, so is it okay that we'll actually make a correction? So this is circumferential stress, sigma C. When you substitute this 2, then you get the circumferential stress as PD by 2T. Okay, this is the first part of the derivation where you derive this sigma c is equal to PD by 2t. Now if you want to derive the second part of the equation, then okay, shall I erase this? Okay, so now for longitudinal stress, again consider the cylinder along the length like this, Okay, imagine that this is going to be cut at this point. Somewhere here it's going to be cut. It's going to be cut somewhere here at this point. So that means at this point I'm going to cut this into two pieces and trying to hold it from both the sides. So here the bursting force will actually try to separate these two cylinders like this, no? Is it not? If I cut the cylinder and still I apply pressure, this side of the cylinder wants to go this side, this side of the cylinder wants to go this side. Have I switched on the... Okay, it's continued. Okay, so this will be the bursting force in the longitudinal direction. The previous one was the bursting force in the circumferential direction. Okay, so now if I say this, then you can understand that the area of the bursting pressure is acting on either side of the cylinder, which is the area here. So that means now the pressure will act on this area. What is this area basically, man? So can you tell me what is this area? What is this basically? What is basically? The diameter. So what is area? So area is pi d square by 4. Pi d square by 4. Now the pressure acts on this. Acts on this. You know pressure is equal to force by area. So force, basically this is the bursting force in the longitudinal direction. Bursting force in the longitudinal direction, Fb, is equal to what? So if you want force, what is force? Force is into pressure into area. So if you want that, then the pressure in the longitudinal direction, P, okay, multiplied by area. What is area? Pi d square by 4. This gives the bursting pressure in the longitudinal direction. And now you will see that now to prevent this bursting, imagine this cylinder has got a thickness here. So this metal along this direction will try to resist this bursting. Okay? So therefore, here we know that sigma is equal to P by A or force by A P by A or load by area or force by area. So force is equal to sigma into area. So you can say that this side of the cylinder will experience what is called the longitudinal stress, sigma L. Earlier it was sigma C. Okay, so this force is equal to this force which is trying to hold this together is called as the stress in the longitudinal direction. That is the internal resistance in the longitudinal direction, sigma L into area. Now can you tell me, one equation was this which is now which is referred. Okay, got this area. But can you tell me what is this area? Can you tell me what is this area basically here? This area I am asking. So can you tell me what is this area? So what I will do is, now this area, I will imagine this to be cut at one end, actually unfold it like this. Unfold into a lengthy strip like this. What is this basically? Thickness T. Okay, thickness T. What do you think is the length here? Pi d. Right now? So if you try to open this and unfold this into a thin strip, it will be pi d. Okay? And then, so here the length is pi d, this is thickness. So I can write this as the force which is trying to resist bending is sigma L into area, which is pi d t. Okay. What? Okay, now once we have done that, we can now equate these two equations here. So this is the force which is trying to resist the bursting of the cylinder in this direction. This is the bursting force. This we can call it as the resistive force. Sorry, I forgot this word resistive force last time. Maybe I'll have to remake this video. So resistive force here. So bursting force equated to resistive force. You can call this equation as 3. You can call this equation as 4. Or this equation that we derived, you can call it as 3. This equation you can call it as 4. This equation you can call it as 5. So equating this 4 and 5, from 4 and 5, you can see that it is bursting pressure is equal to P into pi d square by 4, which is equal to sigma L. So sigma L can be written on the left hand side. It becomes easy for us to handle the equation. Sigma L into pi dt equal to this. Okay. Now here, what and all cancels out, guys, here? So sorry, here I can write it as capital D or small d, whichever which is left to you. So pi and pi cancels out, and this d square will cancels out. So what is finally left here? Sigma L is equal to what? PD by 40. So longitudinal stress in a thin cylinder is given by PD by 40. So in this way, you may have questions in the examination to derive the circumferential stress and the longitudinal stress. And also people may ask you, show that circumferential stress is 2 times the longitudinal stress. So then in that case, what you have to do? Circumferential stress is this one. Circumferential stress is this one, that is the equation 3. You can call this as equation 6. So equation 3 divided by equation 6. Equation 3 divided by equation 6. So equation 3 is what? PD by 2t. And equation 4 is PD by 40. So here PD cancels out. So you can say that it is 40 divided by 2t. So here it is 2 times. So you can say that when you write this equation 3 by equation 6, equation 3 is basically what? Equation 3 is sigma c. Equation this is sigma L. So when you write this, you get this as 2. So sigma c divided by sigma L is equal to 2. So you can say that circumferential stress is 2 times the longitudinal stress. Usually it is given for 6 parts. So I think it's a very common question in the examination. So please try to remember this. So these are basic fundamental, I think almost from basic equations that we already know. We are trying to solve this derivation.